heard a question before about being creeped out from using large language models, querying GPT, etc. So what I will be talking today about is how are we using privacy-preserving techniques, privacy-preserving machine learning, in order to give some sort of confidence in the access of those GPTs, those large language models, and how we're trying to use cryptographic constructions like fully homomorphic encryption, multi-party computation, in order to bring the practicality of privacy-preserving machine learning. So if we think about the key challenges today that we have in accessing those large language models, especially the ones that we have on the cloud, the first challenge that we have, or the first problem that we have, is the query leaks. And these are the privacy concerns that come with inference, with prompts, and with queries. In the current deployments, basically the users, they send their queries to the cloud. In most cases, you have confidential data that is actually included in those queries, and confidential data that is in the inference results as well. So whatever happens on the cloud and how the data is leaking to a third party is something that's not under our control. Besides the fact that there is privacy breaches, the fact that this happens today limits on how we can use those large language models in applications. So if you think about how corporations are concerned about potential breaches, the leaks of sensitive information, etc., this limits how these are used in hospitals, in critical infrastructures, in entities that deal with sensitive information day in, day out. And also this will limit the applications or the personal applications that we can build on top of these models. The second problem is the data leaks when we're doing training. Obviously, for training AI models, whether these are localized models or aggregated models, there is large amounts of data that are being used in order to train the models. And whether we're talking about neural networks or we're talking about large language models, this data basically is also subject to privacy concerns. And even if we're using federated learning, and today most federated learning is being used outside the context of privacy preserving, there is also the risk of data being leaked from the local models that are being used in this overall FL model. And then the third one, and we've heard about verifiability quite a bit, is the verifiability on which model is being used. So today, if you access ChatGPT through the application or through other APIs, you get your inference result back. However, how can you have a verifiable computation or verifiability proof that indeed this is the transformer architecture that is supposed to give you back your result, or this is the actual model that is supposed to give you back your results? So what I would like to spend the next half an hour on is how we are using in TII today, but overall as a research community, cryptographic constructions to address the first two problems: the privacy concerns that result from inference and the privacy concerns that are related to the data that is being used during training. So the first chapter is how are we using fully homomorphic encryption or homomorphic encryption and multi-party computation to achieve privacy in inference. For those in the room that are not familiar with fully homomorphic encryption, fully homomorphic encryption is unlike traditional encryption methods where you have either symmetric keys that are being used to exchange confidential information or the public-private key setup. Fully homomorphic encryption is used in order to process over encrypted data. The research on FHE has started or has become known since Gentry's seminal work in 2009. Today, we have four main FHE candidates. There is BGV, there is FV, FHE over Taurus, and CKKS. Of course, in this application where we're using fully homomorphic encryption for inference and in the context of machine learning, we need to use the ones that work with vectors of complex numbers, of real numbers. Since BGV and FV require encoding of fixed-point arithmetic, which leads into arithmetic circuits being the more and more complex, we use CKKS for machine learning applications. On top of that, CKKS actually allows packing. And then we also use TFHE, which one of its main properties is fast re-encryption and bootstrapping, which basically enables processing over neural networks of many layers, or actually of multiple depth, and also works with nonlinear constructions such as activation layers. So the way that private inference works with FHE, I think let me just start by stating one limitation. If we are to use private inference with FHE, whoever hosts the model or the model owner that's providing this cloud service has to enable FHE within the model. So it's not something that we can use in isolation without having to work with the model provider in order to integrate FHE or in order to be able to run fully homomorphic encryption on it. So the idea is that the query itself is encrypted. This query is sent to the AI provider. The AI provider trains the model the usual way. However, it has to enable FHE requests in order to come back with the query or with the result of the prompt in an encrypted way as well. It sounds easy. However, today, the simple response is this doesn't work with large models. And for those who are familiar with fully homomorphic encryption, they are familiar also with the problem that we have is that there is a high computational inefficiency in them. They're very slow. So the first technology limitations that we're working on using hardware acceleration, especially on the matrix triples, is that computational complexity of FHE schemes has high latency, and then there is high computational complexities and significant memory consumption as well. In addition to the fact that today FHE encryption incurs ciphertext expansion, meaning that each bit in the ciphertext requires many bits in the ciphertext, which impairs the usage over low bandwidth networks. So in particular, networks that are related to IoT or other low bandwidth networks. However, this is an area that is being pursued. Today, there are, let's say, multiple frameworks that are available by the providers that are pursuing this line of research and are trying to bring this line of research to being practical and to being used. There is Concrete by Llama, which mainly includes support for TFHE and provides APIs for machine learning applications. CryptoLab was founded by the inventors of CKKS, and also they hold the patent on the scheme, and also they're trying to provide the APIs for those. You have OpenFHE and HELib that are also available in the open source. They're trying to have multiple, somewhat fully homomorphic or fully homomorphic encryption schemes all aggregated within one library. Now, given the limitations in the performance of those fully homomorphic encryption, there's a lot of work that is happening on the hardware acceleration. So you see entities like DARPA that are calling for efforts of, let's say, main players in order to accelerate fully homomorphic encryption, especially on acceleration of the discrete Fourier transform. So we have, there is the DARPA data protection and virtual environments where you have main players like Intel, Nobium, and Duality that are following through with this hardware acceleration. There are also other companies like Fabric, Cormani, etc., that have developed new architectures to speed up FHE. However, today the benchmarks don't exist. And this is, again, an area of research that is continuing to be worked on. What we are doing today in TII is that we're trying to bring this to a practical applications. So what you see over here is, and I hope that the video works, we're developing a framework to create mobile applications that process data in an encrypted form. We have an FHE-based neural network classifier, we have the mobile UI, we have the neural network compressor, and this is an FHE plugin. It's based on CKKS in this case. And we want any data in the form of text or in the form of images to be processed in a privacy-preserving manner through this setup. So what I will show you here is a very basic proof of concept in order to classify classifying spam or classifying phishing text into this FHE-enabled anti-phishing application. However, in parallel, we're working on another application for the classification of medical records or cancer images, in fact, and we're hoping also to open source part of this application. So I'm hoping that the video can work, even though it's a basic video, but at least it will give you some flavor of what is being done. And the process through this application is basically what I explained over here, is that this encrypted data or this encrypted phishing email or phishing text has been processed through the FHE plugin. It went to the neural network classifier. The results came back in an encrypted format, and then they were decrypted and then provided back as the classification result was provided back to the user. In addition to using fully homomorphic encryption for inference privacy, we're also working on the usage of multi-party computation schemes for private inference as well. Also, to just as a simple explanation of multi-party computation, in a multi-party computation protocol, whether in this context or other, basically data is processed in a distributed manner and in an uncentralized manner. And in this way, basically one party that has access to only one part of a key or one part of the information cannot guess more than the obvious about the entire, let's say, universe of information or about the other party's input beyond what can be inferred from the output. Unlike FHE, today MPC has an acceptable performance, and the only thing that is, let's say, different, or the only disadvantage of MPC is that it is interactive, and this is why it requires several communication rounds, but computational-wise, it is much more computational friendly than homomorphic encryption. In terms of the state of the art and the MPC protocols that exist today, there are numerous ones. In terms of circuits, there are arithmetic circuits that can be used, and usually this works well with linear layers. And also there are Boolean circuits that work well with linear layers, and then arithmetic circuits that work well with activation functions and non-linear layers. The other distinction or the other classification of multi-party computation protocols is we have the active security protocols and then the passive security protocols. The active security protocols, you think about it, that you have some parties or some players that are participating in the protocols, and these are the hostile ones or the malicious ones that are able to deviate from the protocol and then actually change the behavior. And in the passive and in the active security ones, usually you can have better proofs of verifiability. Whereas in the passive security protocols, this is where the dishonest parties, basically what they can do, they can leak memory or they can leak data. However, they don't try to attempt a change of behavior of the protocol or of the parties and the protocol itself. And this is why today, in most of the, ultimately for the private inference, you need an active security of the multi-party protocols that we have for better security levels, for better guarantee of delivery as well. So I guess the private inference with MPC is self-explanatory. The fact that you can perform private inference with an AI provider by providing multiple parts of the query through an MPC protocol or through distributing it through multiple servers, as you see over here. The main bottleneck here, as I mentioned before, is not the computation. It's more about the communication delays and the fact that this computational delays or the communication requirements can make those protocols slower. Usually MPC protocols, when they're used for private inference, they're used as a mix of Boolean circuits and arithmetic circuits, where the Boolean ones work on activation layers and the arithmetic ones, they work on the linear layers. Let me skip this one. There are multiple frameworks that exist today. One of the frameworks that exists is the EasyPC Microsoft framework, which works basically on 2 parties. So it is limited to 2 parties today, whereas Meta has published Crypt10, which is based on arithmetic circuits and secret sharing. And today it is one of the most adopted or the most widely adopted frameworks for a private inference using MPC, and it has a PyTorch-friendly interface. I think the most famous one, I don't know if some of you are familiar with it, is Leuven's COSIC, which is Scale Mamba. And we have based our work in TII, and it is actually an open source work at TII that we call FANG, for privacy preserving or inference privacy using multi-party computation. This is, as I mentioned, it is a continuation of Scale Mamba, which today as an open source software is not supported anymore. So this is why we have taken it as the base of what we have in FANG. In terms of the comparison with CryptGen today, FANG reduces the required trust, and it allows for a more efficient MPC framework. It offers active security with a dishonest majority in a 2-party setup. So this was related to the privacy in terms of the inference or in terms of the queries and the prompts. The second part that we are addressing, also using a combination of multi-party computation and homomorphic encryption, is private training via federated learning. So how are we merging federated learning with privacy preserving FHE and MPC in order to have privacy? So today, when you think about training, so the federated learning, in the federated training or the federated learning training setup, you have data that is localized, so it is in distributed entities. Local models are being generated, and then you have an aggregation of AI models. In the case of where we introduce FHE and MPC, we're basically taking off the security at this layer and that layer. The problem with traditional federated learning today is threefold. The first one is the privacy with respect to the aggregated model over here, and the fact that the final model, if you don't have the right privacy setup, will leak individual training data. The second one is at this layer, which is also privacy with respect to the local models. Also, same concept is that the information at the intermediary layer of the models could leak information as well through inference attacks on those locally trained models. And then the third one is a trust at the federated learning participants. At the end of the day, you're also trusting each of the local or the distributed entities to actually distribute or to contribute the model that has been trained at each one of them. So how are we addressing each one of those problems? The first one is the privacy with respect to the final model. And this is where we are using approaches. This is basically the data extraction. So we are trying to mitigate against the threat of extracting data from the training model, from the final model that can be done via the membership inference attacks. And what we're doing here is we're combining differential privacy with federated learning. And the idea is that there is noise that is being added against the data extraction from the final aggregated model, but of course this will come at a reduced accuracy and reduced utility of the final model that is being generated at the node. I think one of the most famous frameworks that is open source when it comes to combining differential privacy with federated learning is Flower. This is also another one that we have taken in TII, and then we have added privacy using this differential privacy, and this is the private Flower framework also that we have contributed. The second one is how can we use fully homomorphic encryption in addition to federated learning in order to ensure privacy at the local models or the intermediary models in order to avoid the fact that they could be data extraction from these models as well. Usually if it is, let's say, a simple aggregation like using the average fed or fed average, any homomorphic encryption model that can be used for more complicated or more complex ones, we use fully homomorphic encryption or leveled fully homomorphic encryption. And basically what we're doing is that we are enabling another or an additional layer of fully homomorphic encryption in order to solve the problem of disclosing information from the locally trained models. And then the last one is, the last problem that I mentioned before is how can you actually trust that each of the local entities is contributing the model that has been generated or the model that has been trained on the data. And this is more traditional defenses where basically the rogue model that is contributed or a suspected role model that is contributed by a local entity is compared basically to other models submitted by other entities or a golden image of that. So if you think about the model as a multidimensional vector, you can use cosine similarities in order to do this comparison. What we're doing is a different approach, let's say. So we are using a new federated learning framework enabled with multi-party computation, and we are submitting it to the open source hopefully later in the year. So this allows an aggregation of an n-party models or models that are generated by n parties without having any performance degradation. The good point about it is today it has been tested with large language models up to 7B in terms of parameters, but of course this was, and I assume this was a limitation of the computational power available, and we're hoping that this will increase, or the number of LLMs that we can process through this aggregation framework using MPC can increase. The first version has a passive security for the multi-party computation protocol that is being used. It is compatible with PyTorch, transformers, and TensorFlow. And our first release would be with the large language models that we have developed internally or locally at the Institute, which is the Falcon series. Next year, we will be working on active modes of security of the MPC protocols that are being used. We will add to it differential privacy and also model poisoning detection. So maybe before I conclude, I would like to show you more the combination of the Petal Guard, which is the MPC framework for model aggregation used with the federated learning or privacy-preserving federated learning, and then the FANG framework, and then how we're positioning it together.
The rapid evolution of artificial intelligence will lead to exponential growth in the next decade, with direct impact in new paradigms such as smart cities, smart manufacturing, e-health, autonomous driving, among others. However, this growth is fed with data. It takes vast amounts of data to train large machine learning models, which can be scattered among countless entities and protected by diverse privacy regulations. Also, the massive size of large ML models makes deployment on the user side unfeasible, thus pushing AI to the cloud service paradigm, forcing users to send private data to the cloud. This has fostered an unprecedented interest in privacy-enhancing technologies applied to machine learning such as differential privacy, generative models, fully homomorphic encryption, and multi-party computation. Big corporations such as Meta, Google, Intel, or Microsoft have fueled research on efficient private AI, and TII has recently joined this race. TII has developed an open MPC platform for machine learning. It enables private federated learning among different entities. Model aggregation is secret shared, protecting each entity's dataset. TII's platform also allows private classification using neural networks. Users can benefit from cloud-based AI without relinquishing privacy. The MPC platform is optimized for machine learning algorithms. It's equipped with efficient protocols for convolutional layers, matrix multiplications, and neuron activations. It also counts with hardware-accelerated, fully homomorphic encryption to pre-process MPC computation. It allows the full separation of the MPC pre-processing from the online data processing, enabling a separate set of entities to run the FHE engine. TII's platform provides native integration with databases and existing machine learning frameworks. It will be open source and publicly available for the AI community. TII will continue working towards a more trustable and private AI.
I think with this, I would end my talk. Just one word is that all of these frameworks, they're accessible. They're all on GitHub. So if you would like to go and explore and include them in your applications, would be encouraged to do that.
Thank you so much, Dr. Aaraj, for the great presentation. We have time for questions, if we can take questions.
There's a question at the back.
This one.
Thank you, Dr. Najwa. My question is, what are the areas where we need significant improvement in FHE in compared to the other traditional approaches?
So you mean in the FHE itself, or
Right.
more about using FHE for including the privacy? I think if we're talking about the usage of FHE for privacy preserving, today the main, let's say, limitation of FHE is the computational complexity and then the time that it takes in order to process a specific operation, right? So this will be the main limitation today. This is why, one, on the algorithmic side, they're looking into improvements, but also on the hardware acceleration, basically implementing parts of the FHE algorithm and hardware on FPGAs for acceleration is another area that is being pursued. If you're talking about the usage of the model itself without FHE and basically without any limitation on the security or on the privacy, as I presented today, you have the FHE approach in order to the combined FHE and MPC approach for the training security or federated learning or the aggregation of this model. You also have the FHE approach and the inference security, and also the MPC approach that we're adopting for the inference security as well.
Thank you.
Please.
I have a question. In your use of MPC for inference, you're imagining that you are splitting the query among, let's say, three. I think in your picture there were three. So how are you imagining that playing out? Who are these three entities? You're imagining a company that's outsourcing LLMs, say, to divide up into three parts that you're trusting are not going to collaborate with each other?
It's a great question, and this is part of the applied aspect of deploying these technologies. Think on the inference side, one collaboration that you need is from the cloud provider or from the model provider that is hosting this. So in our mind, let's say in the active security model, we always assume that you have a specific number of players that are the dishonest player, and these could be like servers that you can assign yourself. But you also need the other players that you can trust, so it's the trusted players. And typically in a scenario where you have the model hosted by the model owner, our vision is that these will be servers that are also assigned by the model owner as well. So this is how we see at least the deployment model. To give you an example of that, today we are deploying this. We have, let's say, large language models that we have developed at the institute, and we're also developing a marketplace on top of that. So that's easy because we own the model, we're hosting the model, and we're providing these marketplace services on top of it. So we assign the players where you would be the MPC players, basically, or the MPC parties, we assign them. However, if today we're going to go to another, I don't know, Mistral or GPT or wherever, you would need to go and talk to them in order to assign other players that are distributed, where you would be doing the MPC computation or basically there will be the different parties and the MPC protocol.
What are you trying to hide from? You're trying to hide your query from the model owner, no?
You're trying to hide your query from the model owner, yes?
And now you're trusting the model owner to assign the servers on its behalf, some of which he says it gives you a fraction that you should trust are honest?
I mean, the fact is, the way we see it is that you still need some servers, or at least to give the reassurance for the model owner, you still need some parties to be assigned by the model owners, and then other parties that we assign that the model owner can say is the dishonest players, they can be other players. So it could be assigned by us, or it could be basically a node or a server that you can dedicate to be a party of this MPC. And in that case, even if the model owner only has few players or few parties of the MPC, it will not be possible to recover all the information by having these few parties out of the entire parties that you need for the MPC aggregation.
So I, as a user, will take my query, I'll send it in pieces to a bunch of servers. Some of them were assigned by, I'm trying to understand.
Yes.
Some of them were assigned by the model owner, who themselves I don't trust to begin with. That's why they had the whole other thing. Some of them are actually chosen by me.
Yes.
So I do trust them to some extent. And they will be doing a protocol on my behalf, which amounts to asking the question I wanted and get back the answer, but without the model or the servers assigned to the model being able to reconstruct my query.
So the user themselves, as a user, we send a query. Then you will have the processing, or basically the processing application, which is developed by you or which is developed by the security provider, that will split it into those different parties. Those different parties, some of them could be with the model owner, and the rest would not be by the model owner. Then you will send them to the model. You get the query response in pieces, and then it is up to this aggregator to aggregate and then send it to you as a user as the query or the response to your query. At least this is the model that we're envisioning today as a practical application, and also to get the model owners on board with you in this scheme.